Well, hi everybody and welcome back. Today in this video we're going to continue our work with complex numbers, and up until now we've been representing a complex number like this, and we've called that Cartesian form. And if you think about what's happening if you draw it on the Argand plane, here's my complex number z, and the way we represent its coordinates x and y is that if we go down to the real axis, then this distance here is the x coordinate, or the x part of the complex number, and if we go across to the imaginary axis, then this coordinate is the y coordinate, so that's the imaginary part of our complex number. And we've seen how to do arithmetic and so on with a complex number in Cartesian form. But today we're going to look at something a little bit different, and if you think about, again, putting our complex number here, z, instead of reading off its x and y coordinates, what we're going to do is we're going to think about this line segment that joins the complex number to the origin, and we're going to represent the complex number in terms of its distance from the origin and also by the angle theta that you have to go through to reach that interval that I've just formed. So the first thing we're going to do is talk about the distance from the origin to the complex number z, and I'm sorry that this is not in the right place. So the distance from the origin to the complex number is called the modulus of z, and we denote the modulus of z in the same way that we denote the modulus of x when we're thinking about x being a real number. And when we're along the real number line, if this is our point x and we think about mod x, then it gives us the distance that we have to travel from the origin to the point x. If the real number that we're looking at is a negative one, so maybe we've got minus x over here, then mod of minus x is still the distance from the number to the origin, and so that's why we end up with a positive distance there. So we're thinking about this as a distance. So we're going to use the same idea when we're looking at the modulus of a complex number, but of course now we're not directly along the axis, we're coming out from the origin to the point z that we've given just here. But if we write the complex number still in Cartesian form, then we can use Pythagoras to find out what the modulus of z is, in the same way we did for thinking about the length of a vector. So here's my point z, it's got coordinates x and y, or x is the real part and y is the imaginary part. So there's my y, here's my x. And so if I'm thinking about the distance from the origin to that point z, my complex number, then I can take the square root of x squared plus y squared using Pythagoras theorem. So if I've got x squared plus y squared, that gives me that distance squared. So the modulus of z is given by the square root of x squared plus y squared. So that's how we find the distance from the origin to the complex number z. Okay, so when I started talking about this, I said we needed to think about the distance from here to the complex number, but also the angle that we have to go through to get to that interval that joins the origin to our particular complex number. So when we're thinking about the angle, we call the angle the argument of z, and we denote it by arg z, and it's the angle that z makes with the positive real axis in the complex plane. So we've got our point z here, and we join it by a line segment to the origin, so that gives us that line segment from here to here, and we're measuring from the real axis around to that line segment, and the angle that we measure is theta, and that's what we mean by the argument of z. So how are we going to determine what the angle theta is? Well, if you have a look at the picture, you'll notice that this is right angle triangle in the complex plane, and that's representing a right angle, not an R. And if you think about our angle theta here, we know that tan theta is equal to the opposite side over the adjacent side. So if we're thinking about the opposite side over the adjacent side, then in terms of the coordinates that we have, the distance on the opposite side is just y, and on the adjacent side it's just x. So we have tan theta equals y over x, where remember the complex number z is equal to x plus I y. If it turns out that theta is in the first or the fourth quadrant, so remember what that meant when we were thinking about trigonometry. So we had a circle that looked like that, and this was the first quadrant, this was the fourth quadrant. So if it turns out that our complex number is either in this upper quadrant or this lower quadrant, then we can conclude that theta equals arctan of y on x, so we can write it like that, because remember the range of arctan is between minus pi on 2 and pi on 2, so that's why we can think about it like arctan if we're in those two quadrants. But if we're in these two quadrants, we have to be a bit careful, because arctan isn't defined for values from pi on 2 around to 3 pi on 2. So that's just a small point. We need to think a little bit carefully about writing this in terms of arctan. Okay, so that's the argument of z, but of course we need to be a little bit careful because the argument of z is not unique. So what do I mean by that? Well, if this is my complex number z, then the angle that I'm reading off starts at the real axis and goes around to that interval that I've drawn from the origin to z, and I'm looking at tan theta equals y on x, or theta equals arctan of y on x in this example. But I can also go all the way around to pi and then a little bit more. So if I were to go all the way around from here through theta and then an extra 2 pi and come back to that line segment, then tan of theta plus 2 pi would give me the same y on x. So we have to be a little bit careful. We could actually go around as many times as we liked and we'd still get the same answer. So we need to be careful that we don't write down things that are going to confuse us all. So the convention is that we write the angle theta from minus pi to pi. So not including minus pi, you'll see that's a strict inequality, but including pi. So our theta should be some angle that is less than or equal to pi, but greater than minus pi. So if our angle is in the first quadrant or the second quadrant, we measure the angle in that direction. But if the angle is in, or the complex number is in the third quadrant or the fourth quadrant, we measure the angle in that direction. So that's a bit of a messy diagram, but you'll see what I mean as we go through. Okay, so let's try an example. So what we want to do is we want to find the modulus and argument of these complex numbers. So we'll start with number 1, and we're looking at z equals 1 plus root 3 I. Okay, so I strongly recommend that you draw a picture, just a very simple picture, to show where the complex number is, because remember I said if the complex number is in the first quadrant or the second quadrant, we're going to measure the angle that way. But if the complex number is in the third quadrant or the fourth quadrant, we're going to measure the complex number that way. And it's sometimes easy to lose track of where your complex number is. So just doing a rough sketch like this shows me where which quadrant my complex number is in. Okay, so what I have to do is find the modulus and the argument of this complex number. All right, so remember we said if z was a complex number in Cartesian form, x plus iy, then the modulus of z was just equal to the square root of x squared plus y squared. So in this example, my complex number is equal to 1 plus the square root of 3i. So the modulus of z is equal to the square root of 1 squared plus root 3 squared. So this is just equal to the square root of 1 plus 3. And we're only taking positive square roots here because we're measuring a distance, so we don't want that to be a negative number. So the modulus of the complex number is 2. And then we want the argument of z, and the argument of z is equal to theta, where tan theta equals y over x. Okay, so in our example, so the argument of 1 plus root 3i is equal to theta, where tan theta equals y, which is just root 3, over x, which is just 1. So this is root 3. So we need to find theta such that tan theta is equal to root 3. So we need to go back to our favourite triangles. If you don't remember how to do this, remember the triangle that had pi on 3, root 3, 1 and 2 on the hypotenuse, and then this angle was pi over 6. So we want to find the angle that has the opposite over adjacent being equal to root 3. So the opposite, root 3 is opposite pi on 3, 1 is adjacent to pi on 3, so this means that theta is going to be pi on 3. So tan pi on 3 is equal to root 3 over 1, which is just root 3. So that means our angle theta is pi on 3. Okay, so that's how you find the modulus and argument of a complex number. Have a go at these ones. We'll talk about these when we come into class on Thursday. And remember, draw a picture and theta has to be an angle from minus pi to pi. Okay? All right, have a go at a couple of questions before we move on to the next part of this topic.